Welcome to the talk. The title of the talk is Near Linear Approximate Emulators for Planar Graphs. I am Zihan, and this is based on joint work with Hsien-Chih Chang and Krauthgamer. So graph compression is a mean seen in graph algorithm for decades. The input is graph, and the goal is to compute a smaller graph that faithfully captures certain features of the input graph. For example, the flow information, the cut information, the distance information, effective resistance, etc. Okay. The word smaller has different interpretations. For example, if we fix the set of vertices and allow the set of edges to be smaller, then what we are getting is actually an edge specifier. If we really allow the set of vertices to be smaller, so instead we do not fix the original set of vertices, instead of compute a smaller graph on a smaller set of vertices, then what we're getting is called a vertex specifier. The focus of this talk is vertex specifiers that preserve distances, and in particular, the emulators. Okay, that is, the input graph is large, but we are only interested in a small subset of vertices in it, called terminals. And the goal is to construct a small graph that contains these terminals and preserve the distances between them in the original graph. Okay, so in addition to the emulators, there are other objects that have been extensively studied. For example, if we do not require the output as a graph, but instead it can be any data structure, then what we are getting is distance oracles. Okay, and if we just fix the set of vertices and require the set of edges to be a subset of the original edge, then what we are getting is spanners, and this is indeed an edge specifier. Okay, so in the past decades, many outstanding works have been done on these topics. So for emulators, usually there are also some other additional requirements for the output graph. Since if there's none other additional requirements, then we can simply output the click on terminals with the edge weights given by their pairwise distance in the original graph and be done with it. Okay, so a natural requirement is that the output graph has to have similar structure as the input graph. For example, we may require that the output graph is a minor of the input graph, and this is called distance preserving minors. Okay, so in this talk, we focus on constructing emulators for planar graphs. So if the input is a planar graph and we want to output to also be a planar graph, but not necessarily a minor of the input graph. Okay, so we are not computing a distance preserving minor, but just a planar emulator for a planar graph. Okay, so it turns out that this relaxed requirement is sufficient for many algorithmic applications for our emulators. Okay, so there are two parameters that we like to optimize. The first one is the distortion. So basically the output graph for every pair of terminal, the distance must be within a factor alpha from the input graph. Okay, so this is called distortion, and sometimes it's also called stretch. Okay, and another parameter is the size of graph h that we output. Okay, the size is measured in terms of the number of the vertices in it. Okay, and also the number of edges in it is also a valid measure for size, and they are within the constant factor, so we do not distinguish between them by a lot. So ideally, we want the distortion to be as close to 1 as possible, and the size to be as small as possible. And the previous work just studied the trade-off between these two quantities. Okay, so let's look at some previous results on this emulator construction. So the previous work by Krauthgamer, Nguyen, and Zondiner focus on the case where the distortion has to be 1. Okay, so if we're only interested in the output graph exactly preserving the distance between terminals. Okay, so they provide an upper bound of t to the 4. Okay, so t is the set of terminals, and using the notation, we also use t to denote the size of the terminal set. Okay, so it is the size of the terminal to the 4th. Okay, and this upper bound also holds for general graphs. Okay, so for every graph, there's a emulator that exactly preserve the distance of this size. Okay, and in the same paper, they provide a lower bound of t squared, and this only holds for this even holds for planar graphs. Okay, so on the other hand, if we just require that the output graph only contains the set of terminals, okay, then there's a long line of work that eventually leads to an upper bound of log t in the distortion. Okay, and actually this result also holds for general graphs, and they are actually outputting a distance preserving manners. So in particular, this specific setting, they call it standard point removal in some literatures. Okay, So the upper bound is log t, and the lower bound is at least 2, and this lower bound holds even for trees. Okay, so these are these two interesting settings. And there's another very interesting setting that is what if we require the distortion to be 1 plus epsilon for an arbitrarily small constant epsilon. Okay, so in this setting, the previous work by Chang, and Hsien-Chih showed the upper bound of t squared over epsilon squared. And the previous work by Krauthgamer, and Zihan shows the lower bound, which is t over epsilon. So there's still a quadratic gap here. Okay, and our results is that we provide a improved upper bound in this setting, which is the dependence on t is linear. Okay, so the bound is t polylog t over poly epsilon. Okay, and in addition to that, this emulator can be constructed in near linear time. Okay, so n over poly epsilon time. Okay, so this O tilde hides polylog t factors, and this O tilde hides polylog n factor. Okay, so since it can be computed in near linear time, it comes up with some applications. So it will imply faster algorithms on approximate mean SD cut, approximate diameters in planar graph, etc. Okay, so we will not be talking about this application, but only focus on the construction of our emulator. Okay, so the construction of our emulator consists of 3 steps. So in the first step, we consider a special case where all the terminals lies on the boundary of one face. Okay, so we assume that we are given a planar embedding, and there's one face in which the boundary contains all the terminals. And we call this instance one hole instance. Okay, so the first step is we construct a near linear size emulator for the special case, one hole instances. And we use this result to deal with the case where the number of holes that contain all terminals is not 1, but a constant. Okay, so constant hole instance. We use the one hole result to develop the same result for constant hole instances. And eventually we use the constant hole emulator to deal with the general case. Okay, and the size is always the near linear in T. Okay, so the second step, third step. And first step is focusing on this one hole instance. And it turns out that the most technical step is the first step. Okay. So in the remainder of the talk, we will first briefly describe the second and the third step, and then come back to the first step. Okay, let's now first look at the third step, in which we assume that we know how to construct an emulator for the constant hole instance, and we want to deal with the general case. Okay, so in this step, we use a very powerful tool in planar graph algorithms, first developed by Friedrichsen and Klein Moses Sommer, called the R divisions, or sometimes R divisions with constant holes. Okay, so R division is a decomposition of a planar graph into n over R subgraphs called pieces, which may share edges and vertices, such that every edge in the original graph is contained in one piece, well, at least one piece. Okay, and each of the piece contains at most OR vertices and O squared of R boundary vertices, where the boundary vertices are the vertices in this piece that also appears in some other piece. Okay, so for example, if this is the partitioning, then this black vertices are the boundary vertices. Okay, and also O1 holes. What do we mean by that? For each piece, the planar embedding induced by the original embedding of the original graph has this O1 hole property. So all the boundary vertices lies on the boundary of constant faces, okay, or constant holes. Okay, so this is R divisions with O1 holes. So in fact, what they show is that for any R, such a decomposition exists and can be computed in linear time. Okay, so for our purpose, since we have a set of terminals in the graph, so we managed to add one other condition to the R division. That is, each piece contains approximately TR over N terminals. So basically, the terminals are also evenly distributed in these pieces. Okay, so this is just by a simple modification of the original graph, that the original algorithm that proved this R divisions here. Okay, so how we're going to use this R division? We start with an exact emulator of size T to 4 in the previous work. Okay, and we apply the R division with R being T cubed. Okay, and what we will be getting is T constant hole instances, each with T to the 1.5 boundary vertices and O1 original terminals. Okay, so in each of this new instance, we will view these boundary vertices and terminals as new terminals, and we construct an emulator using the O1 hole algorithm. Okay, with respect to these new terminals. Okay, Since there are only O1 terminals inside and all the boundary vertices lie on the boundary of O1 host, it is indeed a O1 hole instance. So we can apply the algorithm for O1 hole instance to it. And for each piece, we get an O1 hole emulator, and eventually we glue all the emulator together to get an emulator for the original graph. Okay, so what are the size? We get T such pieces, and each of the piece has a T to the 1.5 emulator. So the total size is T to the 2.5. Okay, so starting from T to the 4, we get a T to the 2.5 size emulator that is has a loss in the accuracy by epsilon. Okay, and what we're going to do next, we just repeat this argument like for a few steps more. Okay, so starting from T to the 4, we get a T to the 2.5 epsilon emulator, and we do the same, get T to the 1.75 2 epsilon emulator, and eventually we manage to reduce the size to near linear. Okay, so on the surface, it seems that this trade-off, in order to have like near linear size, we need to have epsilon log n emulator. Or if we scale the epsilon, then the dependence on epsilon in the size bound is like exponential. But in fact, with more careful analysis, we can show that the dependence on epsilon is actually polynomial. Okay. So for this detail, you may want to read the paper for more. But this is just showing the ideas how to recursively reduce the size to near linear. Okay, so this is the third step, and let's now look at the second step, where we reduce the constant hole instance to one hole instances. Okay. So in this step, the operation is also very simple. We basically repeatedly cut the graph open along some shortest path that connect two different holes and reduce the number of the holes by one. Okay, we iteratively do so until there's a one hole instance, and we apply the one hole algorithm to it. Okay, so for example, if this is the drawing of the planar graph, and these are two holes that contain terminals on its boundary, and these 4 red vertices are terminals on the boundary of this face. These 3 are terminals on the boundary of this face. And this green path is the shortest path connecting this terminal to this terminal. Okay, and we would like to cut the graph open along this green shortest path. Okay, so in order to preserve the distance between these terminals, what we actually need to do is to additionally introduce a subset of vertices on this green path called portals. Okay, and we want to view them as new terminals and also preserve their distances. Okay, so in fact, what we'll be doing, so how do we select this set of vertices is we will be computing epsilon covers. Okay, so this notion of epsilon covers, we will revisit later in the first step. Okay, so epsilon covers only introduce a linear number of new portals. So basically cutting the graph open along this shortest path, we will incur a constant factor blow up in the number of terminals. And since the number of holes is just a constant, eventually when we reduce the instance to a one hole instance, the number of terminals, the blow up is also only a constant. So we'll be fine with it. Okay, so for example, when we cut the graph open, this is basically what the resulting graph looks like. So this path is duplicated as 2 copies, and these copies of portals are viewed as new terminals. Okay, and these 2 holes are merged into one. Okay, and we basically apply the one hole instance eventually to get an emulator and iteratively gluing back the cut open passes. Okay, so what about the gluing back operation? It is also simple. Basically, we want to just glue this 2 copies of the same path back to the original 1 copy. Okay, but there's one point that we need to be careful with. So we do know that this terminal appear on in the eventual emulator, but these other vertices on this path, they are not terminals. So they are non-terminal vertices. They do not necessarily appear in the emulator that we get. Okay, so basically these vertices are just maybe not there. But what are there is the segment of the boundary segment of the face. These are there. Okay, so what we really do is we, instead of gluing the passes back to their original image, we glue the boundary segments at their portals. Okay, so what we'll be doing is like gluing the corresponding copies of the terminals, and this 2 red becomes 1 red, this 2 red becomes 1 red, and the portals becomes just 1 copy. Okay, and then the portals, when we add in the previous step, are no longer marked as terminals. So eventually we still get back just the set of original terminals, and eventually we get an emulator for the original instance. Okay, so this is the reduction from constant hole instance to one hole instance. And this is the second step. Okay, so in the remainder of the talk, we will be focused on the first step, basically constructing an emulator for the one whole instance, which is the most technical contribution of our paper. So the idea is still to repeatedly cut the graph open along shortest path, and it's a divide and conquer step. Okay, so we repeatedly split the instance into smaller and smaller instance until the base instance are small enough. So we apply some trivial algorithm on it, compute emulator for each of them, then bottom up glue them all together. Okay, but now when we do the cut the graph open along some path operation, instead of reducing the number of holes, we want to now recursively reduce the number of terminals in each of the resulting subinstance. Okay, so at least we want the number of terminals to decrease by a constant factor every round. So every step we decompose the number of terminals also decrease by a constant factor. So we'll be focusing on just describing this decomposition step. Okay. So similar as previous operations, we still need to select a pair of terminals, compute a shortest path connecting them, and select a set of vertices in the path as portals, okay, and view them as terminals in the subinstance. And this is because if we do not add portals, then for the top instance, we can preserve the top pairwise distance. For the bottom instance, we can preserve the bottom pairwise instance. And we glue these two emulators together, this top-down distance may not be preserved. Okay, and in order for them to be preserved, we have to add portals. And the previous work uses epsilon covers, okay, which is notion first proposed and studied by Thorup in 2014. Okay, and it's defined as follows. Okay, so for a terminal V and for a shortest path P, an epsilon cover of V on P is a set S of vertices in P, such that for any other vertex U in P, if we go from V directly to U, or we go from V first to some vertex in the epsilon cover S and then to U, then these two distances are within 1 plus epsilon from each other. Okay, so basically for every U, there's some close by vertex S in the epsilon cover, such that like directly go from V to U or taking a detour through S is within factor 1 plus epsilon from each other, the total distance. Okay, and it turns out that this property is enough for our purpose. Basically, we cut the graph along, we cut the graph open along some path P and view the epsilon cover as new terminals, then gluing together an emulator for each of them gives an emulator for the original graph. Okay, so how many portals do we need to add if we use the epsilon covers in this case? So it has been shown by Thorup that for all terminal P, for all terminal V, for all paths P, and for all parameter epsilon, we can compute an epsilon cover of V onto P with size 1 over epsilon. Okay, but if let's say the original set of vertices, the number of terminals is K, then the top part, let's say it contains K over 2 terminals. If we do it for every single terminal, then we will be adding K over epsilon portals on this path. And if we just cut it open and the top instance has K over epsilon terminals now, and so is the bottom instance. And this is not good for us. We want to decrease the number of terminals, but now we have more terminals. Okay, so this way of adding portals is not good for us, and we will need an alternative. Okay, so intuitively, the epsilon cover is like a local way to find portals. Specifically, if for every terminal, it computes a set of vertices and they take the union of them. Okay. And our alternative is to find the portals in a global way, called exponential portals. Okay, so let's say we find a pair U prime of terminals, and this is the shortest path connecting U to U prime in graph. Okay, so intuitively, the set of exponential portals simply contain all vertices in the path that are at distance 1 plus epsilon, 1 plus epsilon square, 1 plus epsilon cubed, etc. from U, and all vertices that are at distance 1 plus epsilon, 1 plus epsilon square, 1 plus epsilon cubed from U prime. Okay, so we let the set of portals be the union of all these vertices. Okay, so basically in the middle range of the path, the portals are sparse, and the close to the endpoint, the portals are dense. Okay, so for the portals computed in this way to work out, we need one more requirement. Okay, that is the initial selection of the terminal pair must to be like the closest 1 over 4 balanced terminal pair. Okay. So what do we mean by that? So these two terminals separate the boundary segment into two consecutive segments, and each of the segments has to contain at least k/4 terminals. Okay, so t/4 terminals. Okay, basically one-fourth fraction of the terminals. Okay, and among all such pairs, u prime must be the closest pair. Basically, the distance between them is the smallest among all such pairs. Okay, so why is this requirement just sufficient for us? So let's look at some top-down terminal pair. Okay, so let's say V is the terminal lies on the top segment, and V prime is the terminal lies on the bottom segment. And this blue path is the shortest path connecting V to V prime in the original graph. And this blue path intersect the U prime shortest path at a single vertex W. Okay, so we can first show that the distance between V and U is at least either the U prime W distance or the U W distance. Okay, so if it is not true, then we can show that either VU or VU prime is a closer 1/4 balanced terminal pair. Okay, so assume without loss of generality that the top segment contain more than t/2 terminals. Okay, so basically, if this does not hold, then either UV or U prime V is a better choice of the terminal pair, and that's just a contradiction of the requirement that we start with. Okay, so the distance of W is like at least, for example, just say at least a U prime W distance. Okay, so according to the way that we select the portals, there must be some terminal, there must be some vertex, some portal S, such that the U prime S distance is within 1 plus epsilon factor from the U prime W distance. Okay, so basically, if we now just artificially let the shortest path connecting V to V prime to take a detour through S, then the distance loss is at most epsilon factor times the V W distance, and therefore epsilon factor times the V prime distance. And therefore, this just does the job of preserving the distance up to 1 plus epsilon factor if we just add these portals. Okay, so how many portals do we need to add in this way? It turns out that according to this 1 plus epsilon exponential way of putting portals, the number of portals we need to add is log 1 plus epsilon to the ratio between the max distance over the mean distance in the metric. Okay, so actually max terminal distance between over mean terminal distance. Okay, and this is also called the spread of the terminal metric, and sometimes it's also called the aspect ratio. Okay, and therefore, if this ratio is sub-exponential in T, sorry, it should be T. So it's a sub-exponential in the number of terminals, then we're just good because we are not adding a lot of portals, and we are okay with just the resulting instance to be like further decomposed. Okay. So the only remaining case is when the spread is super large. It's like, let's say the spread is larger than exponential in k to the 0.9. Okay, so in this case, let's first make some observations. Okay, so let's say this group of 6 terminals is very close to each other, and these 4 terminals are relatively close to them, and the remaining 7 terminals are very far from. Okay, so now look at this inside-outside pair. Okay, so for example, look at this terminal and this terminal. And let's say this orange path is the shortest path connecting them in the original graph. Okay, so since the distance between them is very large compared with the diameter of this cluster, then if we just artificially let the shortest path to take detours through U and then go to this terminal, then the distance will not be changed by a lot. Okay, and in the ideal case, within a factor of 1 plus epsilon. Okay, so really for this like far away terminal, no portal is needed for it. We just cut the graph along this shortest path and just recurse on the remaining subinstance. Okay, so the portals we really need to put there is for this close by vertices, close by terminals, because they are already relatively close to this cluster. If the shortest paths have to be artificially direct to U prime or U, then the distance just may be changed by a lot. Okay, so the observation is that portals are only necessary for this close by terminals. And actually what we will be doing is just compute epsilon covers for each of them. Okay, so this observation suggests the following algorithm. So we take arbitrarily a terminal U and classify all the remaining terminals according to their distance from U, okay, into layers. Okay, so for example, the first layer contains all the terminals that are at distance from 1 to k from you. Okay. The second layer is from k to k squared. The third layer distance k squared to k cubed, etc. Okay. Since the spread is at least exponential in k to the 0.9, the number of layers we get has to be at least k to the 0.9 intuitively. Okay, so if we can find a layer that is sparse on its own, so this yellow layer is sparse on its own, it has just a few terminals, and also partition the remaining layer into two parts that are at least a constant factor away from k. Say let's say this blue area contains at most 0.9 k terminals, and this green area also contains at most 0.9 k terminals. Then we can just carry out the same plan. Basically, disengage the blue area from the remaining terminals by cutting the graph open along some shortest path, and then adding the epsilon covers of the yellow area terminals as portals onto this shortest paths. Okay, since the yellow layer is sparse, the number of portals we add is small. Okay, and we are done in this case. So in fact, this blue area may not just appear on the consecutive segments as shown in the previous slide, but they may appear on, for example, the two segments, and they just span this blue area. But what we will be doing is exactly the same. Okay, so for every yellow terminal, a yellow area terminal, we just compute epsilon covers onto this corresponding shortest passes. That will be cutting the graph open along. Okay, so this is in the good case where we can find such a yellow layer. But what if we cannot find such a balanced sparse yellow layer? Okay, so actually, since the number of layers at least k to the 0.9, a sparse yellow layer must exist. But it is just possible that none of them is balanced, in the sense that for every sparse layer, one side of the layers just contain very few terminals. Okay, and it may just happen in reality because it's possible that the original graph just partitioned the terminals into constant size clusters, and each cluster is very far from every different cluster. So no matter what terminal we start with, we will be getting a picture like this. Okay, so very few terminals in the first few rounds and all blank rounds, and all other terminals appear on the same last round. Okay, so in this case, we cannot find a balanced yellow layer. So basically the whole layer finding algorithm need to be designed in a more delicate way. So what we'll be really doing is compute a hierarchical partitioning of all terminals by their distances, and carefully select the clusters. Okay, one cluster selected as the blue region, and its sibling is selected as the yellow region, and the remaining part is selected as green. And we carry out the same thing. Okay, so cut the graph open along the blue area shortest passes, and for every yellow area terminal, compute epsilon cover onto it. Okay, the same thing. Okay, so it's just need to be done in a delicate way. Okay, so this summarizes the first step and also summarize the whole algorithm. So to summarize, our main result is a near linear size 1 plus epsilon emulator for planar graphs, and it's also computable in near linear time. Okay, and therefore it has applications to faster algorithms in computing approximate mean cut, diameter, etc. So there are several interesting open problems. So first, whether or not we can remove this polylog factor is interesting questions to ask, and I believe we can. Okay, and also the dependence on epsilon, can we just improve it to just epsilon square or something like that, a small constant in the exponent? Okay, and there's another very interesting question, which is what about the exact emulators? Okay, so when the distortion has to be 1, the upper and lower bound still hasn't matched yet. Okay, the upper bound is t to the 4 and lower bound is t squared. There's still a quadratic gap here. Okay, that's all I'm going to talk about today. Thank you very much for listening.